Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about, or I have defined what is the log functions, and then I was talking about the multivaluedness of my small log functions. Then I said that so out of multivalued functions I should now define is the what is called single valued functions. That means from small log now I will define the principal logarithm. So I have defined the small log. Now I will talk about what is called principal logarithm and its properties, and then we will see like couple of properties of principal logarithm, and then it will have a like what is called it will give you the concept of what is called branches, branch cut and branch point, that I will talk about. And then later I will talk about the notions of Riemann-Stieltjes integral, then continuity integral, path independency and Cauchy-Goussard theorem for this whole week. But for today's lecture my plan is to talk about, since I have defined small log, now I am going to define what is called principal logarithm, and a couple of properties I'll talk about that, and then I'll discuss what about the branch cut or branch point. Okay, so as I said, so now I have defined my small log functions, and you have seen that it is a multivalued functions. Now my next plan is to how to get a single valued functions out of this multivalued function. So that portion I have discussed. So I want that, suppose this is my small f multivalued function, so I want a capital F which is single valued. On top of that I demand that this single valued function should be analytic. For example, I have a small log functions, so one takes these many values, this point takes this many values. So the point is what values I should take to get a single valued functions, and it will have some extra properties like continuity or analyticity. Let's see. So it boils down to the concept of what is called principal value of logarithm. Now you have a log function small log, principal value logarithm means capital log. So small log is multi-valued, then capital log, which is the principal value of logarithm, this is a single valued functions. Now look how I define it. Now you can easily guess it actually, because if you remember the definition of small log, so small log is nothing but ln of mod z plus I small arg of z. Now you can easily say that you replace by capital arg of z, then it will be single valued, right? So that exactly I have done it. So we can make the multivalued functions logarithm into a single valued functions by restricting my small arg suitably. And what is that? This is the principal value of logarithm. That means for z is non-zero, we define the principal value logarithm as capital log z. What is that? This is ln mod z, this part you keep as it is. Now small arg you should replace by capital arg, where your small arg, so I have defined, so given a complex number, I have already talked about what is small argument and what is principal argument. Small argument is a set value, principal argument means you take one value which lies between minus pi to pi and you can have it actually. And small z goes to principal argument of z or capital arg of z, it says single valued functions, okay. And I talked about it is defined on the whole complex plane except 0, but it is not continuous on the whole complex plane. But if I take out the negative real axis including the origin, it is actually continuous, okay. So therefore if I have a small log functions, I can easily define a single valued function which is capital log, and which I am defining it as ln of mod z plus I capital arg of z, where capital arg is the principal argument. Now look, then I said that since capital arg of z jumps 2 pi I at z crosses negative real axis, so therefore it is discontinuous along the curve theta is equal to pi. That I already discussed, because you see I have defined my capital log. It will have two parts. One is the natural ln of mod z and one is the capital argument of z. Now this portion is nicely, very nice. So z goes to like ln of mod z. You can check that this is a continuous function, so you do not worry about that. This is very perfectly all right. But the problem you will have, z goes to capital arg of z, principal argument. So it is defined on the whole complex plane minus 0, but I already proved you that it is not continuous in the negative real axis including the origin. Because if I approach a point in the negative real axis two different directions, that means one from the upside and one from the downside, that means one from the second quadrant and another from the third quadrant, both approaching to the same point but the corresponding principal argument approaching to the different point, I already talked about. So therefore since capital log involve my principal argument and principal argument is not continuous, so therefore to talk about the continuity of a single valued functions for the multiple corresponding which comes from the multivalued function small log, that means I have to somehow delete what is called negative real axis including the origin. That means I have to restrict my domain, and that domain I can say that yes, my function is nice, in fact it is continuous. Later on you will see in fact this is actually analytic, okay. So that exactly. So therefore since small arg of z, if you remember you have an argument like minus pi to pi. So this is minus pi. So this is 0 to pi. This is minus pi. So therefore, if I start from here and if I come back here, so as long as this portion is not there, my principal argument is very nice. It is a continuous function. But that moment I crosses my negative real axis, it jumps. It jumps by what is called 2 pi I. That means you lose the continuity. So that's exactly I am saying. Since small r object has this property, so therefore capital log of z jumps 2 pi I at z crosses negative real axis, and it is discontinuous along the cut theta, and theta is equal to pi. So therefore you have a minus pi less than theta lesser equal to pi. Theta is equal to pi will give you the negative real axis. So theta is equal to pi will give you the negative real axis. So that means to talk about the continuity or analyticity, somehow I have to remove the theta is equal to pi. So therefore I have to restrict my domain. So therefore, however, it is continuous in the domain. You see, d z is equal to r e to the I theta, r is positive. Now this time I am saying that theta runs from, theta is strictly greater than minus pi, strictly less than small pi. So therefore, to talk about the continuity, I need this kind of domain. But to define from multi-valued to single valued, I can include theta like minus pi less than theta lesser equal to pi. That I can include it just to define a single valued functions. But to talk about the continuity, I have to remove this part. Okay. So that's how I have defined my capital log. Now look, this is very important. So it is important to observe that the principal value of logarithm, that means capital log of z, can be defined in the domain. See, this domain I can define it. So therefore, what is this domain? This domain actually, my theta runs from minus pi, but it can take the value theta is equal to pi. That means it is the whole complex plane except the origin, right? However, to talk about the analyticity or continuity, it is analytic in the domain d star. That means you have to remove theta is equal to pi part. That means if I take this kind of conditions, that means d star z is equal to r e to the I theta, r is positive and theta is strictly greater than minus pi and strictly less than pi. That means you have the whole complex plane, but you do not have it the negative real axis include the origin. And if I remove that slit from the complex plane, in that domain, your functions, my functions capital log actually analytic functions, and if I take the derivative, it turns out that it is exactly equal to 1 by z for z is in d star, like in the classical logarithm you know, or the real logarithm you know. So therefore, so now I have a small log, now I am having a principal logarithm. Principal logarithm defined on the whole complex plane minus origin, but to talk about the analyticity of these single valued functions, I have to take out negative real axis including origin. There my function capital log of z is analytic function, and if I take the derivative, it will give you 1 by z. So this is kind of statement you should remember. So this is like computing principal value of logarithm. So therefore, if I just in questions or in exam, if I ask, okay, given this complex number z, calculate what is small log of z, what is capital log of z. Small log of z, if you calculate, it will be multi-valued, and capital log of z, it will be single valued. So a couple of examples I have given. So for example, log 1, so this is ln1 plus I of argument of 1, but argument of 1, if you calculate, this is 2k pi I. So that means at scale running over z, it is taking multi-values, but if I take capital log of 1, so that means principal argument I have to take, that means 0 for argument for the point 1, its principal argument theta is equal to 0, so therefore log of 1 it is taking the value 0. Similarly, you will have for minus 1, you will have argument of minus 1, this is actually pi, pi you can have it theta is equal to pi, so therefore your capital log is this set value, but a small log is this set value, but capital log is exactly equal to pi I. Similarly, you will have small log of minus I, capital log of minus I, you just first write ln of this argument of minus I, but what is argument of minus I? So you can have it, so 2k pi, this part if you take it out, I think 3 pi by 2, I think maybe this is the one. So, okay, so therefore or pi by 2 I think, yeah. So this should be theta, so that means what? So you just have to find out, okay. So therefore your small log of z, you can have it ln of mod z plus I small arg of z. And this is same as ln of mod z plus I principal argument plus 2k pi, okay. So you have to just calculate what is the corresponding principal argument of this complex number 1 minus 1 I minus y. So these are a couple of examples I have talked about. So this is a set valued functions, but however this function is single valued and which is exactly equal to this kind of form, okay. So this is the kind of computing principal value and what is called normal logarithm, that means small log and capital log. Now this kind of ideas, if I talk about in general sense, so it will give you the concept of what is called branch cut and branch point. What is that? So suppose you have a multi-valued functions fz defined on a set D subset of C. Now what is my definition of a branch? So look at very carefully. I am saying that a branch of a multi-valued function f is any single valued functions capital F, but it is just not the single valued functions, but fz that is analytic in some open connected set D star inside D, so that at each point z the value capital fz is one of the values of small f. So that means you have a what is called multi-valued functions in some domain D. So then first you get a single valued functions capital F on domain D, and then I demand that single valued functions capital F need not be analytic on the full domain D. But if there is some subdomain D star there, if my function is analytic, then I will say that this is a branch. So that exactly I have written. A branch of a multi-valued functions f is any single valued functions capital F that is analytic, that is very important. So that is analytic in some open connected set D star inside D, such that if I have point z inside D star, so my capital F of z is exactly equal to one of the values of small z. So the requirement, look, so this is very important. The requirement analyticity prevents capital F from taking and random selections of values of f. So that means you have to select, like for example, small log. Small log you can have it capital log, right? So capital log I can define what is called principal logarithm in capital arg of z. But to talk about analyticity, I cannot have whole complex plane minus 0, but I have to take out the slit. So therefore, if I take out the slit or negative real axis including the origin, there my function is analytic. So therefore, capital log or principal logarithm is a branch of small log. So okay. So what is the branch cut? Branch cut is that now branch is clear. So branch means from single valued or from multi-valued we have a single valued, and in some subdomain if my function is analytic. So that means in my subdomain means I have to take out some portion of the domain, and there I can talk about the analyticity of my single valued functions. So in that way you can say that a branch cut is a portions or a line or a curve that is introduced in order to define a branch capital F of a multi-valued functions. So that means given a multi-valued functions you have a single valued functions, but in that single valued functions it is defined on the full domain, but if I cut a portion of my domain and there my function is analytic for the definition of branch, and that cut portions or line or some curve, that one is called the what is called branch cut. For example, you have a small log, right? Then I can have a single valued functions capital log, and this function is defined on C minus 0, that is perfectly alright. But to talk about analyticity I have to cut this negative real axis including the origin from my domain, and this is actually the branch cut of my functions capital log of this multi-valued function small log. So therefore you can say that this is a branch cut for this one. So that's exactly I have written. So a branch cut is a portion or line of a curve that is introduced in order to define a branch. So therefore to talk about, or I will say that given a multi-valued function small log of z, this is actually a branch. That means I have to take out a portions of my domain, and what is that? This is negative real axis including the origin. This is actually a branch cut of my multi-valued functions small log. Any point which is common to all branch cut, it's called the branch point. Now this is one branch cut. So given a small log, capital log, which is the principal value logarithm, and principal value, why it is principal value I am saying? Because it is defining in terms of principal argument. That is why I am talking about this principal value. Okay, I have written, I think this is I have said, right? So right. So principal value means actually since I am defining in terms of principal argument, that is why I am saying that is principal value logarithm. Okay. So therefore principal value logarithm, to have the branch principal value logarithm of a given multi-valued function small log, the negative real axis including the origin, it is actually the branch cut. Then you can ask, can I have another branch of my multi-valued function small log? Later on I'll tell you, yes, you will have another branch where the negative real axis include the origin need not be a branch cut. You will have some other line including the origin, it will be a branch cut. So there will, in fact I will talk about what are the branches of my multi-valued function small log. So therefore, there we will have another branch cut for some other branch. Now if I have intersections of all the branches, this is called the branch point. That exactly I have written. Any point that is common to all branches. So first I have to see, given a multi-valued functions, what are the branches are there, whether finitely many or infinitely many. Then you have to check out what the branch cut corresponding, and if I take the intersections of all branch cuts, the whatever point it is there, that is called the branch point. So note, so points on the branch cut of f are singular points, and it is quite clear, right? Because just think about small log is a multivalued functions. Now you have a principal logarithm capital log. Now to talk about the analyticity, I have to remove negative real axis, include the origin. That means my function's capital argument, which is not even continuous in that line. So therefore my function is not analytic. So therefore these are the points where my single valued function's capital log has a singularity. So that's exactly I have written. Points on the branch cut for f are singular points, because I'm taking, you have to take out to talk about the analyticity. So therefore my function has a singularity in their branch cut. So this is like a picture I have drawn it, okay, multivalued function, branches and branch cut. For example, this is your domain, okay. So now this is my small f, which is multivalued function. Suppose it is taking this value, this value, this value, so this is value, this one value, this is, these are the many values these are taking, but this is in domain. Now to talk about single valued, it might be defined on the full domain, but to talk about the analyticity, I have to somehow cut something. So this is my branch cut. If I cut this portion, the corresponding image will be this one. So therefore, if I have to take out this one, so therefore on this domain, except this one, it is taking the values 1, and this is single valued, and there my function is perfectly alright, and it is analytic. So this is one of the branch, and the corresponding branch cut is here. Similarly, if I have another one, this is another branch, then you will have the corresponding branch cut, okay, here. So similarly here. So this is kind pictorially I tried to kind of visualize that this is my z plane, this is my w plane. You have a multivalued functions, so you can pick one single valued functions, and you can take, or I will say that single valued function is a branch, provided I have to take out some portions of my domain, and that is actually called the branch cut. So this is the pictorially you can have it. Okay, so this is the principal branch of small log, that's some kind of properties, okay. So the functions more on this principal logarithm. So principal log or principal logarithm of z, that means capital log of z, which is defined as small log or real log of mod z plus I principal argument of z, which I can write is ln r plus I theta, where theta runs between minus pi, but this time strictly less than pi, okay, because it is a branch. That means I demand that analyticity. So this is defined on this star, is a branch of my multivalued function small log. It is okay, I written here. It is called the principal branch. Why it is principal branch? Because it uses principal value of small log. That is why it is called the principal branch. I will show that it will have many branches, but this is the principal branch because it is it deals with what is called principal argument. For the principal branch, okay, what is the branch cut? The negative real axis including the origin, that means this set, L is a set of all z x plus iy, where y is 0 and x is lesser or equal to 0. This is actually the branch cut. So that means this is my domain, so this is the portion is the branch cut, and this is the corresponding principal branch I have kind of in the picture. So therefore you will have minus pi to pi, but it should not cross what is called negative real axis. So this is the kind of picture I have drawn it. So the principal branch of multivalued function small log. Now there are many branches, right? So this is the one, all branches of log z, you can have it. So what is that? It says that, so take alpha belongs to R, the single valued functions, if I define in this way, in that domain, it is actually a branch of my function small log. What is that? Now look, so alpha is in R, I am defining f alpha of z, which is f alpha of r u to the I theta, if z is equal to r u to the I theta. I am saying that this is ln of mod r plus I theta. Now look, what I am saying is that this time z belongs to this set d alpha star. What is d alpha star? It is the all complex number z where r is positive, of course, but theta runs from alpha minus 2 pi to alpha. If theta runs from this set, then this capital F alpha is a branch. So it's a branch of my multivalued function this, and this function is also analytic here. Now you can say that this is the kind of all branches. Why? Because now if I take alpha, alpha is a real number, na? So if I take alpha is equal to pi, then what it will give? If I take alpha is equal to pi, so this is f pi of z, this is the definitions. But look at the domain. What is my domain? Say d pi star. So this is actually also z r e to the I theta, where r is positive, and look, theta running from what? If I put alpha is equal to pi, so minus pi less than theta less than pi. And what is that? You can remember the domain. This is nothing but my principal logarithm capital log of z, right? So if I take alpha is equal to pi, then capital F pi, this is nothing but capital log. So this is for particular case. But if I take alpha is in r, so that alpha varies over r, it will give that many branches. So therefore it will have uncountably many branches of my multivalued function small log. For each alpha in R, it will have a branches capital F alpha. But what is interesting fact is that what is the for this principal logarithm, what is the branch cut? Theta is equal to pi. Now here I will have this set where this is my capital F alpha is a branch, and in this domain it is analytic. So what is the corresponding branch cut here? Theta is equal to alpha. So that means if I have a complex plane, suppose this is my alpha, so if this is my line theta is equal to alpha, so therefore for these branches capital F alpha, what is the branch cut? Theta is equal to alpha. That means this is the ray theta is equal to alpha including the origin. So if I consider theta is equal to alpha, that ray including the origin, this is the corresponding branch cut of this branch capital F alpha. That's exactly I have written. For each branch capital F alpha, the ray with angle theta is equal to alpha including the origin, that means this is the one, z is equal to r to the I theta, theta is equal to alpha, r is positive including the origin, this is a branch cut. For example, if I take theta is equal to pi, then you will have theta is equal to pi. Theta is equal to pi means what? This is the negative real axis. It is a branch for capital log z, or this is same as capital F pi, same of z. Okay. So therefore, if I vary alpha is in R, for each alpha is in R, I have capital F suffix alpha. That means you will have uncountably many branches of small log for the multivalued functions, and for these branches capital F suffix alpha, the corresponding branch cut is the ray theta is equal to alpha including the origin. Now what are the intersections of branches or branch cut? It is the origin, because all branch cut it is the ray theta is equal to alpha. In particular, if alpha is equal to pi, it will give you the principal value of the logarithm, and it includes the origin also. So therefore all branch cut it's a ray including the origin. If I take the intersection, origin itself. So therefore for the multivalued function small log z, the branch point is the origin. So therefore origin is the common to all branch cuts, and it is the branch point of the small log. So small log has its branch point is 0. And what are the branches? Branches are uncountably many. That means if I take any alpha is in R, this is the function corresponding the branches, but you have to be very careful about the domain. Domain should be all those z where R is positive, but theta runs from alpha minus 2 pi strictly less than theta, strictly what is called strictly less than alpha. So that means alpha minus 2 pi is strictly less than theta, and theta is strictly less than alpha. So you should not have the equality here. If I have the equality, then you will lose the what is called analyticity. So what about the branch cut? Branch cut is the what is called ray theta is equal to alpha including the origin. What are the intersections of all branch cut? That is the origin, which is a branch point. So this is all branches of my functions small log multivalued functions. So that's exactly, I just summarized this discussion. So all branches for each alpha. So these are the branches, capital F suffix alpha r to the I theta, which is ln r plus I theta. R is positive, theta runs over there. Branch cut is the ray theta is equal to alpha include the origin. Branch point is the z is equal to 0. So that means you can like multiple branches, like as I said. So that means from minus pi to pi, if you have it, then there either you have it, but the moment you cross the negative real axis, it should jump. That means you are in the second floor. That means you will have this branch. Then again there you will have like two-dimensional things. The moment you cross the negative real axis, you will end in the third floor. So these are the kind of multiple branches of my function small log. Okay, so identities involving principal logarithm, like identities involving principal argument, principal argument like principal arc of z1, z2, it is not exactly equal to principal arc of z1 plus principal arc of z2, if you remember, that is there. So similar kind of principal logarithm you can have it. Capital log of z1, z2 is in general not exactly equal to capital log of z1 plus capital log of z2, because it involves principal argument, and which kind of fails to satisfy this kind of properties. However, if I have restrictions on my complex number z1, z2, then it satisfies. That means if real part of z1 and real part of z2 is 0, that means if I am in kind of right half plane, that means x plus I z1 is equal to x1 plus i1, x1 is positive in the right half plane, there it is satisfies. And if I take the product log of z1 z2, this log z1 plus log z2 plus you'll have some additive factor 2k pi I for some k is in z. So this is kind of identities you should remember, you can prove it easily. Now once I have a complex functions, exponential function, logarithmic functions, then you can have the power, and that power you can define it. Why? Because x to the power a, how you define it? It should be e to the power a log x, ln x, right? This kind of things you know in case of real. So you can have it e to the power a ln x, right? That you know. So in that way, I have the exponential, I have the logarithmic functions. Now can I have the definitions of z to the a? Answer is yes, you can have it. Look, So now you can define complex exponent or complex powers. So using the logarithmic functions, we can define powers of z. That means I can define z to the power a the way I have defined in case of real. So that means it should be e to the power small a log z, where z is in c minus 0. But now it is quite clear, because I am defining my z to the a in terms of small log, and small log is a multivalued function. So therefore z to the power a, it's clear that it will be a multivalued function. So now therefore I can talk about its branches. Okay. So therefore look, so where a is any complex constant, log z is a complex logarithm. Now first observation is that since small log is a multivalued function, so therefore z to the power a in general it is a multivalued functions. But these are the three nice observations you will have. If a is an integer, then it turns out that this becomes a single valued. Okay, how you can do that? It is very easy. Now z to the power say k. Okay, what is that? In my definition, this should be e to the power k log z. What is that? This should be e to the power k. Now log z, small log, what is the definition? This should be ln of mod z plus I small arg of z, right? That is there. Or what is that? That is same as e to the power k ln of mod z, okay, plus I, then what is that? Capital arg of z plus 2k pi, okay, and what is that? So this should be, okay, this should be bracket, right? Okay, so this is also k. So now just take a is equal to m, integer, right? So what is that? Let me just check. So if a is an integer, I am saying that it is single valued. You can have it. Yes, this is true, because z to the power m. What is that? This should be e to the power m small log of z. But what is that? E to the power m. What is small log of z? You can have it. So ln of mod z plus I small arg of z. What is that? This should be e to the power m ln of mod z plus I capital arg of z plus I 2k pi. Correct? What is that? E to the power m ln of mod z plus I capital arg of z, right? Plus m times I times 2k pi. Correct? But what is that? This should be e to the power m. You can have it. What is capital logarithm? So you can write it. This is capital log of z. You can have it. Then you will have plus, or using the properties of exponential, this should be e to the power I times 2k pi m. But m is an integer, k is an integer. So if k is an integer and m is an integer, so therefore this value will be always 1. So therefore it will exactly equal to e to the power m capital log of z. But capital log of z is a single valued function, so therefore m is fixed, so therefore this is a single valued function. So therefore if a is an integer, this is always single valued. Because if a is an integer, that means it will hit with, at the end it will have 2k pi I. Now k is an integer, a is an integer, so therefore k times a, it will also be an integer, and you will have the value e to the power 2k pi m times I. It will not contribute anything for different values of k, it will be always 1. So therefore you will end up with this kind of single valued functions, e to the power m capital log of z. What about a is rational number? There also you can guess it. It will have finitely many values. Again you can have it. Why? Because you see, so take say a is equal to p by q. Okay, what is that? That means e to the power, or say z to the power p by q, right? What is that? This should be e to the power p by q. Then you have capital log of z, right? And what is that? Then you can easily have it, right? E to the power p by q. Then the way I did this calculation, this should be capital log of z plus I times 2k pi, right? And what is that? This should be e to the power p by q capital log z. You keep as it is, this part, you do not touch it. So then you will have e to the power p by q times I times 2k pi. Now what is that? Now you see, this is, now you just forget about this part. This is actually single value. Now look at here. Now this should be actually e to the power I times 2 pi, and then you will have what? K p divided by q, right? Now, well, you can, there are many ways you can do that. This should be e to the power, you can say that 2 pi k divided by q to the power p. You can think in this way, right? Now look, k running over z. Now if k runs over z, so if k takes from 0 up to say q minus q values, so it will have what? So from 0 it will take one value, 1 to up to q, because q is an integer, so it will give how many values? That many values, finitely many values. And after that, if I take q or k is equal to, I think this should be q minus 1, right? Yeah. So it's up to, so k from 0 up to q minus 1, this will have q many values, right? So if I take k is equal to q, then it will repeat with the value k is equal to 0. Then if I take q plus 1, it will take the values k is equal to 1 and so on and so forth. So I mean this object, it will have q many distinct values, and if I take the to the power p, it will have that many distinct values. So therefore if a is a rational function, so z to the power a, it will have finitely many values, because after sometimes k, even if k is runs over full z, after sometimes it will have actually repeating. So therefore only q many distinct values will be there if a is equal to p by q, because of this fact. But in all other cases, that means if I take a is like not integer and not rational number, it will take you infinitely many values. Okay, so these are the examples I have given. For example, you see minus 2 to the power 5. So since a is an integer, so it will give a single value, and it is indeed the case. So first to define, this should be e to the power 5 what is called log of minus 2. So first you calculate what is log of minus 2. Again, by the definition, it should be ln of 2 plus I small arg of z, and then you can write small arg by principal argument plus 2k pi. So this is exactly equal to ln 2 plus I times pi plus 2k pi, where k runs over z. If I use the definition, minus 2 to the power 5 e to the power 5 log of minus 2, that means it should be 5 ln 2 part that will take out. So it will have only k part, but k part will give you 1, because you are dealing with a is equal to 5. So therefore it is exactly minus 2 to the power 5. What about minus 2 to the power 1 by 7? As I said, it is of the form p by q. Since q is 7, then 7 many values will be there, and it is indeed the case. So log of minus 2, this is okay as it is, ln 2 plus I times pi plus 2k pi, plus minus 2 to the power 1 by 7, by definition is this one. So this part you just forget about that, it will be always single valued. You are dealing with real logarithm, but it will have e to the power I times 2k plus 1 divided by 7 pi. But if k runs from 0 up to 6, so it will have that many distinct values, because if I take k is equal to 7, it will repeat the value equal to 0. So therefore it will have finitely many values. So I have written, so the distinct values of minus 2 to the power 1 by 7 is exactly equal to this one, k runs from 0 to 6. And if I take minus 2 to the power I is not a integer and not a what is called rational number, so it will take infinitely many values. So again, so this is my log of minus 2, you just use the definition, this should be e to the power I log of minus 2. Now you see, so this portion again, it will be single valued, because I am dealing with natural or real logarithm. But look at here, e to the power minus 2k plus 1 times pi, and k runs over z. Now if k runs over z, this is taking, for each k z, it is taking distinct values. So therefore this will be infinitely many values. Okay, for each k in z, this is varies. So therefore it is taking infinitely many values. So therefore it is taking infinitely many values. Okay, so now, so principal branch I can define, okay, like the way I have defined principal logarithm for z. Principal logarithm given a multivalued function small log, I have defined capital log. Now this is a multivalued functions, so I can define what is called principal branch of this one. It will have many branches, because it will be a multivalued function, so it will have many branches. What will be the principal branches? Now it is clear that by specifying branch of logarithm, we obtain single valued branch of a complex power functions of the form e to the power a log z, small log. In particular, if I choose the principal logarithm, it is kind of same way, like since z to the power a I am defining as e to the power a small log, and small log has a principal logarithm capital log, so therefore this will have a principal branch if I define a capital log of z, and this is exactly the case. So in particular, if we choose the principal logarithm capital log, we obtain the principal value, and what is that one? This is e to the power a times capital log of z. So therefore if I replace small log by capital log, this is the corresponding principal branch of z to the power a. So therefore the principal branch z to the power a is e to the power a log z, and it is analytic. Of course, wherever my function's capital log is analytic, or principal logarithm is analytic, theta runs from minus pi to pi, where theta is not equal to pi. That is very important. Not only that, the definitions or the derivative, you know, in case of real analysis, same thing true. That means d dz of e to the power a log z, which is e to the power a log z times this derivative, and it turns out this is equal to this one for z is in distance. So this is the corresponding derivative formula. Now this note is very important. You see, we remark that the above equations can be written in the familiar, like this is the one, you know, if I replace z by x, that kind of, or z or a by some real number, then this kind of derivative you know. So I can think about this also in this way, with the proviso that the branches of logarithm used in defining z to the a is same as the branches of logarithm used in z to the power a minus 1. Because you see, Now if I want to think about this object in this way, that means in the left hand side I am dealing with z to the a, that means one multivalued functions. In the right hand side I am dealing with another multivalued function, that means z to the power a minus 1. So to talk about this equality, now this time I am dealing with multivalued functions, so that means I have to specify what branch, that means what single valued functions I am talking about, then we will have the equality. Answer is that for z to the a and z to the power a minus 1, by the definitions I am dealing with small log. And small log, if I deal with, small log has many branches. So I will have to first fix branch of my small log, and that branch I should work for both z to the a and z to the power a minus 1. Then this equality is true. That means I cannot take one branch of small log to define my z to the a and another branch of small log to define z to the power a minus 1. In that case, this equality might not be true. So to talk about this equality, or to say that this is true, that means the branches of logarithm I am using for or defining z to the a, the same branch I should take for defining z to the a minus 1. Then this is exactly equal to true. So now I have a multivalued function z to the a. Principal branch is that small log replaced by capital log, and the same properties what you know in case of real analysis, that is also true. Okay, so this is actually Riemann surfaces like z to the half. Now z to the 1 by or p by q, it will have finitely many values. Now z to the half, so it will have two branches. So I have written, so two branches fz is equal to z to the half. So I have written it clearly, say a plus this exponential half of ln r plus I theta, where theta runs from minus pi to pi, and this is the f minus another branch. You will have exponential half ln r plus I theta, r is positive and theta runs from minus 3 pi to minus pi. So since z to the half, that means it will have two branches, and you can have it explicit expression of these two branches, and this is called the Riemann surfaces of my function z to the half, because it will take finitely many values, because z to the power p by q, this is 1 by 2, that means two branches are there. Okay. Similarly, you have Riemann surface of z to the power 1 by 3, it will have three branches. So I just try to draw a picture. So this is one of the branch, and the moment you cross your kind of a branch cut, it will shift. Okay, so it will have two branches. So this is 1 and this is 1. What about this one? This is 1, this is 2, and this is 3. So you can think in that direction. So since you have a branch, you will have a corresponding branch cut. So you should not go, or you should not cross the branch cut. So branch cut cross means you go to the upstairs and then upstairs. So again, so Riemann surface for z to the power 1 by 3, since it will have finitely many values, so you will have three branches. Okay, so I think that's all about like discussion about what is called multivalued functions and its branches. Okay, so I have discussed exponential functions, logarithmic functions, small log is a multivalued functions. Then I have defined what is called principal value of logarithm. Okay, so then couple of properties and the known kind of properties, as you know in case of real logarithm, that is also true. Then I have talked about exponential like z to the power a. You know the definition of x to the power a in the real case. Now I have a definitions of small log, exponential, capital log. So therefore I can define what is called that complex exponential, that means z to the power a. In general, it is a multivalued functions because I have defined in terms of small log, but small log, since it is multivalued, so the complex exponential in general it is multivalued, but I can take a single valued functions. It will have branches. So if I replace small log by capital log, it will be the corresponding principal branch, and then depending on the power of z to the a, where if a is an integer, it will be single valued. If a is rational, it will be finitely many values, and if a is not rational or integer, then it will be multivalued. And couple of examples I have talked about, and of course I have discussed all the branches of what is called log functions. In general, if I have a multivalued functions, then I have defined what is branch cut, and what is branch point. I think in my next lecture I'll start discussion. I'll discuss what is called Riemann-Stieltjes integral or contour integrations, and at the end I'll talk about what is called Cauchy-Goussard theorem. I think I should stop here. Thank you.